Okay, so what we're going to do is just a very quick discussion right at the start about what logarithms are, and then we're going to get into the mathematics of it and revise some of the calculations we will do. What I've got here is the graph of 10 to the power of x. Okay, so you've got that sketch there beautifully from Desmos. So y equals 10 to the power of x. And last time we talked about how they would generate that graph, right? And when we first learn about logarithms, we learn about logarithms in base 10, don't we? So if they're in base 10, we don't need to write the base here because log by itself suggests base 10. So if we say, what is log of 50? All right, what is log of 50? Or log of, let's go log of 10 here, and let's go log of 100 here. We're saying, what are these things? What is log of 100? So what we should remember is we have to try and express this as a power of 10. This one we can do, all right? 100 is 10 to the power of 2, and then that would simplify to 2. Once we've expressed it as a single power of 10, it simplifies to the index. Similarly here, we have log of 10 to the power of 1, and so that would simplify to 1. All right? So log of 100 tells you what's the power you need to raise 10 to get 100. Log of 10 tells you what's the power you need to raise 10 to get 10. Log of 50 then, all right, let's work it out. Log of 50, we're going from this graph, 50 is going to be about here, okay? So that's corresponding about here somewhere. That's pretty close to 1.6, all right? So what we're saying is log of 50 is going to be log of 10 to the power of, and I'm pretty sure it's 1.69, we can check on our calculator in a moment, would simplify to 1.69. So the question, log of 50, it means what number do I put 10 to the power to get 50? 10 to the power of 1.69 will give you 50. If we said log of 70, it means 10 to the power of what number equals 70. So that's a bit of a recap of what logarithms do, okay? Then you have, if we continue on to the next page, we have the graph of 2 to the power of x. 2 to the power of x. So the same concept applies, all right? So if we have, and we can alter this graph fairly easily to have 2 to the power of x, that can be 32, that can be 5, those points correspond, and there's more points in here, isn't there? 4, 3, 2, 1. I won't put the y-axis in. But if we have log in base 2 of 32, all right, we want to express that as a single power of 2. We'll have log in base 2 of 2 to the power of 5. Okay? Because this is the base of the logarithm, this is what we have to express the that number in there as a power of 2. So that's going to simplify to 5. So similarly, like, you know, generally we give you ones that you can evaluate as a single power of 2. So another one might be 8. That's log in base 2 of 2 to the power of 3. But every now and then you might have log in base 2 of 10. And so what does it mean? Okay, well here we saw, the question is 2 to the power of what number will give you 32? 2 to the power of what number will give you 8? Here it is, 2 to the power of what number is going to give you 10? And that's going to be some rational number we can evaluate in that case. So that's what logarithms mean. That's where we derive them from, that's where we get them from. Okay, so let's flick over and let's start doing some of the maths of it. So we're going to break this lesson up into 2 parts. We have 1B.1, where we're going to review the laws of logarithms with some operations, and then we have 1B, so we're going to do 1 and 2 together, and then later in the lesson we'll do 3 and 4. So we do have a fair bit to get through today. So to start with, we've just got, I'm going to jump up here for question 1A, write an equivalent exponential statement. So the logarithmic statement is log of 100 equals 2. Okay, what's the base of this logarithm? It is 10. This means 10 to the power of 2 equals 100. All right, we have log of 100 is 2. it means the base of the logarithm to the power of 2 is going to equal this number. It's just like this comment here, all right? If we have log of 50 is 1.69, then 10 to the power of 1.69 is 50. Okay, question B. We've got log in base 3 of 1 on 9 equals minus 2. We want an exponential statement. So we take the base of this logarithmic statement is 3. 3 to the power of minus 2 equals 1 on 9. So you can start to see where I'm getting those numbers from. I'm taking the base goes there. I'm taking this number, that's our power. All right, base is 3, that's our power, and then here's what it evaluates to, 1 on 9, 1 on 9. So that's just reflecting logarithmic statements to exponential statements. Now we're going to do the opposite. We start with an exponential statement, 10 to the power of minus 3 equals 1 on 100. What's the base? The base is 10. So that means we're starting with just the logarithm. What are we evaluating the logarithm of? 1 on 100 equals minus 3. Is that 1,000? That should be 1,000. Let's change that there. Typo. Okay, let's explain why that is the case. And this is going to be one that we're developing a bit. So what we have here is we have 1 on 10 to the power of 3 at the bottom. We can use index laws to bring it to the top with a negative power. And once we've expressed it as a single power of 10 at the top of the fraction, it evaluates to the power. Okay, so you can see that's equal to minus 3 because of this process here. All right. Okay, we've got one more example. We have 2 to the power of 4 equals 16. So this time we have log in base 2 of 16 equals 4. We're jumping from an exponential statement to a logarithmic statement. Okay, so now we're not given a link, we're not given some equation. Now in question 2, we just have to evaluate them ourselves. So let's start. We've got log, I'm going to write them up here to start with. Log in base 5 of 5. We've got log in base 2 of 32. So we need to express this number as a single power of 5. So log in base 5 of 5 to the power of 1. No massive changes there. We've expressed it as a power of 5, so now it evaluates to the power. Log in base 2 of 32 is 2 to the power of 5. We've expressed it as a single power of 2, so now it evaluates to the power. Okay, we'll jump over here for C. We've got log of 1 on 100. Okay, this time we're not given a base, so we assume base 10. We need to express this number as a single power of 10 at the top of the fraction. So we can do it in a series of steps. If you can see it, jump straight to it, okay? But we're going to have 1 on top of 10 squared. All right, 100 we express as 10 squared. We can move it to the top of the fraction by making the power negative. Okay, and now it's a single power of 10 at the top of the fraction, and so it's going to evaluate to the power. All right, might clear first board, just because we want a bit more space to do D, really show those index laws. All right, we have log in base 3 of the square root of 3 on top of 9. So before we can evaluate this, we need to simplify it to a single power of 3. So we need to collect these somehow. Our very first step is going to be express both of them as a power of 3. So we're going to have log in base 3 of 3 to the power of a half. Okay, that's what the top is. The square root of 3 does mean 3 to the power of a half. And 9 is 3 to the power of 2. All right, we've expressed both of them as the same power. Okay, next we're going to do the subtraction index law, because these have the same base. All right, I might write it up here for you. A on A to the M on B to the N. Excuse me. A to the M on A to the N is equal to A to the M taken. So if they have the same base, we do the top power and take the bottom. So this is going to simplify to logging base 3 of 3 to the power of a half take 2. 3 to the power of a half take 2. Alright? And then that's going to become 3 to the power of negative 3 on 2. Alright? Half take away 2 is negative 3 on 2. Now that we've expressed it as a single power of 3, we can evaluate it to the power. Now, every year, I'm always recapping how do we do these sort of fraction operations. It's a skill we do learn like back in year 8, but it's one that I want you to make sure that you're very competent at. So we'll just brush over that really quickly. If I have half take away 2, before I can perform this fraction operation, they need to have the same denominator. All right? So I need to write this number with a denominator of 2. So I'm going to have half take away 4 on top of 2. All right? 4 divided by 2 is 2. And so now that they have the same denominator, what we can do is we can write them together. We can bring them together. All right? And so it's just 1 take away 4 on top of 2. That's negative 3 on top of 2. Minus 1.5. So yep, you get full marks there. You can express it as a decimal if you want. Either of those is fine. I think we tend to prefer fractions, generally speaking. Okay, so that's that one. Then we've got, I'm going to rub this out. We've got log in base 5 of 0.2. Now some of them you just sort of need to see. Like it's not immediately obvious how the link between those two. But the more you do them, the more exposure you get to them, the more you see it's something like this. 1 divided by 5 is 0.2. Okay, 1 divided by 5 is 0.2. So then we can express it as 5 to the power of minus 1. And because it's the base of 5, it evaluates to the power of minus 1. Very good. Okay. Any questions so far? All right, so what have we got? We've got about 5 more to get through. So we've got log of 2 plus log of 10. And so we're using the laws of logarithms that are put in the box there for you guys. All right, so when we're adding logarithms together, what it simplifies to is log of 2 times 10. This is log of 20. All right, and we can confirm that's true a number of ways. We could put log 2 plus log 10 in our calculator, or we could put log 20 in our calculator, and we see that they evaluate to the same value. All right. We have log 120 take log 6. Okay, so when we're subtracting them, it is the top one divided by the bottom one. Log of 120 on 6. All right, 120 divided by 6 will be 20. Now, I might show you why that's obviously true in a moment. Let's move on to C. We've got log in base 2 of 5 plus 3. Log in base 2 of 5, and then we've just got plus this number 3. Now, we want to express it as a single logarithm. That's what the question asks us to do. Express it as a single logarithm, which means we need to write this number as a logarithm in base 2 if we're going to collect them. If we're going to collect them, it needs to be a logarithm in base 2. So, this is what it is, and I'll explain why. log in base 2 of 2 to the power of 3 simplifies to 3. So we're just going back the other way, all right? We're starting with a number and we're expressing it as a logarithm. We know that has to be the base, so we know we're expressing it as a power of 2, so it has to be 2 to the power of 3. So we'll simplify this in 2 steps. Okay, they have the same base, we're adding them together, so that means that we can write it as the product. Log in base 2 of 5 times 8, log in base 2 of 40. We can't straight away just add these together because they're not like terms. They don't have the same value of the logarithm, and they have different powers out the front, different multiple products out the front as well. But one of the laws of logarithms is that if there's a number out the front, we can make that the power of this number here. So we're going to first rewrite it as log of 2 to the power of 3 plus log of 3 to the power of 2. All right, so that's our first step. Is we're moving that product to become the power of the logarithms. That's that's the third law in your box there. Okay, so then we'll simplify them. We've got log of 8 plus log of 9. The same base, so we can bring them together to be one logarithm. We'll have log of 8 times 9, log of 72. Alright, last one. We have simplify log in base 3 of 9 on top of log in base 3 of 81. Now there's two ways we can do this. Alright, I'm going to show you guys both of them. I'm going to show you guys both of them. So one way is going to work across here and the other way is going to work down here. Alright, so here's one way we could do it. We've got 3 squared on top of 3 to the power of 4. So the more you do them, the more you realise, things like 3 to the power of 4 is 81. Basically, we probably should know the first 5 powers of the first 5 prime numbers. Okay, so what's that? 2, 3, 5, 7, 11. Cool. All right, so we've got that. Now, what we can do, because we've expressed it like this, we can bring the powers out the front here. So we have 2 of log in base 3 of 3 on top of 4 in log in base 3 of 3. And you can think about it a couple of ways, like this does evaluate to 1, all right? Or you can think I've got the same thing at the top as I do at the bottom, that's a product, so I can eliminate it. So we're left with 2 on 4, which is half or 0.5. All right, the other way we can arrive at it, we will have this same first step, okay? But then from here, right, they have the base of 3, okay? So we have log in base 3 of 3 squared. That simplifies to 2. And log in base 3 of 3 to the power of 4 simplifies to 4. Okay, so we're just making some connections there. All right, that simplifies to 2, that simplifies to 4, and you get your half again as well. So multiple ways of arriving at that same conclusion. So this is enough to get started on 1B.1, 1B.2. Hopefully it's a bit of a recap. I want to come around and see if you have any questions about it as such. But yeah, hopefully we're pretty confident with logarithms. All right, so 1B.1, 1B.2. Let's get into that in our books. Spend about half hour doing that.